It's an honor to give a talk today. I would like to share some of my work in the past 6 months. I work with the online collaborative learning platform economy to provide a solution doing the silicon validation. Okay. So, okay, that's my brief background. Currently, I'm teaching in 3 universities: Taiwan University, Tsinghua University, and Yangming Jiaoda universities. After I retire from my job via technology as a CTO, I have been working on the PC industry for over 30 years. Yeah, in my past life, I designed all kinds of chipsets and also the processor, x86 processors. Before I retired, 12 years before I retired, I worked on the system area, particularly in storage system. I work on the computational storages. So I'm interested in how to do the efficient computing. Yeah, and since I retire, I'm teaching in university the application acceleration with high-level synthesis. And during the time I teach the high-level synthesis, I talk a lot of system, because I want to accelerate applications. So there are a lot of system issues involved. But most of the students don't have the background on the system knowledge. So that's why I get back to the fundamental and teaching the SoC design, starting from next semester, also in these 3 schools. I also founded the Bridge Your Life Education Foundation, and the purpose is to bridge the technology training school and the link with the school and industries. Okay, this is the agenda of my talk. First, let's talk about why cultivating IC talent and the IC system validation is so difficult. So that's bring to the Google open source silicon programs. So I'm glad that Aaron's talk is before me, because I already give you a lot of background about my talk. And then I would like to tell you about the FSIC development platform. Okay, this is based on the Google open source silicon, especially the Caravel SoC. Okay, and I will touch a little bit about my future plans. Okay, first give you some background. So we all know the China and US trade war and the geopolitics issues. So in the world, people try to establish its semiconductor supply chain and also aggressively develop the design, the semiconductor talents. And Taiwan government also realized that and passed the regulation on the industry university cooperation and talent collaboration programs. So it comes that they established the Institute of Semiconductor in these 4 universities. However, while increasing the quantity of the semiconductor talents, but how do we to improve the talents on its qualities? So that's a very critical issue. And also, I would like to address why it's difficult to cultivate the IC design talent. If we compare with the software open source program to how the software talent is developed as compared with the hardware IC design talent. So we know that to design an IC, you need EDA tools, and the EDA tool is very expensive. And not like a software, you just need to use free compilers. And to make a chip, you need a lot of the IPs. Yeah, but IP is also expensive. You have to pay for the IP before you can start using it. Yeah, and so after chip is designed, you need to tape out. Okay, so all those difficulties actually the Google open source silicon come to address these issues. Okay, and however, if you observe this program and the industry move, the system validation, especially the system level validation, is not addressed. So I'm glad that in previous session a person asked about how the silicon is validated. So my talk is mainly focused on system validation. Yeah, how to easily validate your chip. Okay. So this is a Google open source silicon program. So I won't spend time because Aaron already talked about it. So Google pay for the NRE and maintain the open source EDA tool. Okay. And Efabless plays a critical role that collect everybody's design and send to Skywater for manufacturers. In addition, to facilitate the IC design process and also to validate your design, Efabless provide a so-called Caravel Harness. Okay, the Caravel Harness is basically an SoC. Okay, you have a user project in this area and integrate with the SoC. And this SoC, the purpose of this SoC is doing the management with the your user project, okay? And so you can test your chip using the, you develop the firmware and run in the Riscv in the SoC to interact with the user project, so provide the validation of your design. And also there are, if you pay attention, actually this chip doesn't have a lot of I/O pins, a total 60 pins, okay. Okay. And we see that you have a 38 NPRJ, basically it's the GPIO pins, okay. So you can communicate with the outside. That's all it provides. And the user project going to occupy 2/3 of the die size, and 1/3 is reserved for the management SoC. Okay, so that's a very quick brief on the Caravel Harness. And so after the chip is manufactured, the chip will be soldered on the daughter board. Okay, and the daughter board will be put on the Caravel boards, and you test it through 2 ways. One is using you write the firmware and run in the Riscv processor, communicate with the your user project, or through the 38 general purpose I/O pin. And this I/O pin can be accessed through a connector. Okay, the connector here. Okay. So then you can put on the testing fixtures outside, through the connector to test your project through those 38 general purpose I/O. Okay, and those pins has no bus protocol. It just dump I/O pad. Okay, so it's very hard to do a computation accelerator chip because it needs volume data to come in out the chip. Okay, so those pins doesn't have any bus protocol, so it's not efficient at all. So you can test very simple designs. Okay, so this program with this Caravel SoC, it provides very limited system validation capabilities. Okay, I think it's very good for analog circuit design. Okay, or some simple design doesn't need volume test data. Okay, the system level validation is very, very crucial. Since I have been in the IC industry for over 30 years, and I realized that if a silicon validation is often the bottleneck of the time to the market. So if the chip is not validated completely and you push into the market, and if there's any problem, they're gonna bring a tremendous damage to the company. Unfortunately, the school does not teach it. Okay. And it's very difficult to do the system level validation. There are at least a few reasons. One is the designer does not design the necessary observability and controllability in the design, because those designers doesn't have a system validation experience, so he doesn't know need to pull in the test circuit for observability and controllability. Yeah, and also most of the IC designer lack of a system operation knowledge. The system concept is rarely teach in the school. And also it's very difficult to build a system validation platform, especially in the university environment. It's not like a company that you have a dedicated system team. You can design and manufacture your test boards. Yeah. But it's difficult for the school. Yeah. And I think the most crucial one is the system debugging is often by software means. Okay. So there is a common concept that the hardware designer really don't appreciate software. And also in the school education, they separate software and hardware. Okay, you rarely see any engineer who process both software and hardware capability. Yeah. However, doing the system level validation, you do need extensive software capability. Yeah. So in my company, Viller, so normally, I think that there's a standard process, okay? The IC designer, after it's done, you hand over to the system engineer and software engineer. So software engineer doing all the system validations. Okay. However, the hardware design is a black box for software guys. So it's very difficult for software. And the hardware designer does not know how the software is tested for the system operation. Yeah. So when they design the hardware, they provide insufficient hook for software engineer to debug his hardware. Yeah. So that's all those issues prolong the system validation time. Yeah. So that's why I think so in here. So in system validation, we have to distinguish the IC testing and system validation. Okay, in school, I think most of university offer IC design lab course. Okay, however, they only design, they go through the backend IC design flows, and they design an IP. Okay, the IP never put into the system to test. How do you validate your IP? You use a tester. Okay, and the test program simply, you capture the simulation waveform and translate into a test program and run in the tester. So the tester simply is to validate the manufacturer fault, to make sure the silicon behave as you simulated. And this is really not an issue. In today's the semiconductor technology is so mature, you hardly see, or the PDK2 is also mature. You hardly see that what you simulate does not match the silicon. Yeah. So this IC testing basically doesn't address the system validation. So to do the system validation, you see, you have to design a test board here. And the board has to connect to your system. Yeah, so there's a lot of trouble. Yeah, you need to design the board. And Aaron talked about people use 3D printing to create this board. But how many people in school can access the 3D printing and design the board? It's also time consuming to do all those dirty works. Yeah. And also, you cannot scale up the talent training. Okay. So, for example, if I want to train 1,000 IC designers, can I do this way? Yeah, no way. Yeah. And also, you cannot arrange 1,000 designers come to your tester lab, put into queue to validate your design in tester. So both ways are very difficult to deploy. Yeah. Okay, let me introduce the FSIC program. Okay, my purpose is design a program to train full stack IC designer. Okay, full stack here, I mean the engineer need to have the skill in the IC design, FPGA design, and especially important, embedded programming. And in today's school does teach students embedded programming. However, they use the existing MCU board. Okay, you write some software. Okay, they call that embedded programming. Okay, so when we talk about embedded programming, I mean that you have to do it in the firmware level. And the firmware has to directly interact with your hardware. Okay, and if you write the program using the API, okay, let's say you have a hardware, and then you have firmware, and then you have an OS, and then after the OS you have an API. So you actually develop your embedded program through many levels up. Yeah. So never get a chance to directly write the firmware to interact with your hardware. Okay, so I don't think today's school embedded programming course is what I mean embedded programming. Yeah, it's just a little bit lower level application program. It's still application program. It's above OS level. Yeah. So I very much emphasize the embedded programming. Okay. So to train students with these techniques, I designed a serious hands-on lab based on the SoC level platform. Okay, and thanks to the Caravel Harness, they open source their SoC, so we can directly access our hardware. Okay. Okay, that's the IC validation platform. Okay, in here, this the Caravel chip. Okay, you have a user project area here. Okay, to validate this chip, we put our FPGA here. Okay, the FPGA in particular, we use the MPSoC. That means we have a SoC in the FPGA. Okay, the SoC can communicate remotely with the designer. Okay, and then to facilitate the testing on your user project here, we develop several IP here, and also the IP on the FPGA side. So students can validate their design remotely, okay, basically using the Jupyter Notebook and writing the Python code. And they actually realize using very low cost pink Z2 board. Okay, this PCB, the board, FPGA board, only costs about 3,000, 4,000 NT. Very cheap. Okay, about $100. And we design a small module board with socket. Okay, so when the chip come back, we replace the chip and pull into the socket. And this module board connected through the existing I/O connector. Yeah. So all we did is we just design a module board and with the socket on top of it. So students have the chip come back, they just pull into the socket, yeah, and pull in the central remote lab. And student can access through Ethernet and Ethernet using the Jupyter Notebook. Okay, so that's what you can see here, yeah. Okay. So we have so by doing that, we can scale up the whole training programs. A lot of people can validate their chip. They don't need to have a board on the side. They don't need to struggle with all the software stack to bring out the software, the FPGA stack, all those things. They can start testing their hardware right away. Okay, so how we do that? Okay, that's the following development work is in the last 6 months. I lead a group of about 20 collaborators from academy. Okay, they are free engineering resource. I don't pay for them. Yeah. So I teach them to do the IC design, and I come out a real project for they to work on. So they use this project to learn the IC design. Okay. This is a Caravel FPGA. Okay, that's, I have already introduced the Caravel Harness. Okay, in here, we have look at the user project area. We have those interface. One is the wishbone. Wishbone is the interface that communicate the Riscv to communicate with the user project. And we have a logic analyzer. You can think it's just general purpose I/O pin for Riscv CPU to transfer data to the user project. Okay. Again, the logic analyzer doesn't have any bus protocol, so you use a program I/O to feed the data to the user project. So it's a very slow process. You cannot transfer mass volume data. And this chip doesn't have a DRAM controller. They have only very limited storage here. Okay, only 256 bytes of data, and there is no DRAM interface. Okay, so how do you get the data to your user project? The only way is through there's 38 I/O pins from outside. Okay, as I said, those I/O pins just dumb I/O. There's no bus protocol. Yeah, so that's a Caravel SoC. So how do we do the Caravel SoC simulation? Okay, so this is your design. Okay, and you have those pins. Okay, and you write in the Viller environment, you write Viller test bench. Okay, inside the test bench, what do you do? Okay, first you instantiate the Caravel chip. Okay, and then second, you load your firmware code. In here is a counter LA hex file. That's a basic compiler Riscv executable. And you load into the SPI flash models. And this model going to interact with the Caravel chip through those flash I/O pins. Okay. And the next step, you release the reset. So once this chip, your design, as it from the reset, it start fetching the code through the flash I/O and read your code from the SPI flash memory. Okay. And then the chip start running, and then the phone will interact with your user projects. Okay. After it's done, either your design or Riscv put the status on the GPIO pins, and your test bench gonna to read. Okay, your test bench going to using the check bit to read the pin and see if those pins has the states match your result. If it matches, then your test is passed. Okay. Otherwise, that if over exceed the simulation time, certain time, then it fails. Maybe something hang inside your design. Okay. So that's the simulation environment. Okay. So our next step is turn this simulation environment truthfully to FPGA implementation. Okay, so this is the FPGA. Okay, this is your Caravel chip. Okay, we port the Caravel design into the FPGA, and we implement those IP. Okay, those IP is very simple IP. For example, this Caravel PS. This design only takes like 5 or 6 lines of HLS code. Very simple design. Because HLS provide a lot of facilities that provide all those interface. So only 5, 6 lines of code. It's very small for loop. Yeah. And this IP is allowed you to your test program or the test bench code. You have to rewrite your test bench code from the Viller code to Python code, and this Python code run on the PS ARM processor, and then it provides the API. So that this API can interact with this FPGA design to pass the pin signal state, and you can read it to read the pin status. Okay, yeah. So so the other IP like the ROM code is actually perform the XI master transactions to read your firmware executable from the DDR memory and load it into the block RAM. Okay, and the SPI flash originally translate the behavior model, Viller behavior model into a hardware design. Okay, so that originally that's a SPI flash behavior model. Okay, it's not synthesizable, but however, just modify the code a little bit. Okay, it can be synthesizable and put into the FPGA. So this module will interact with the flash I/O pin to read the data, the firmware code from the block RAM to the Riscv. Okay. So if you recall how the verification is done, the directed translation is this API basically talk to the ROM code FPGA design. Tell the FPGA design to do the master cycle, XI master, to transfer data from DDR to block RAM. And then you control this pin to release the reset. And after it's wrong, remember that the test bench will read the NPRJ pin states, okay, using this API and interact with the IP design to get the pin states. Okay, as you can see, everything is done in hardware. Directly translate from the software Verilog simulation environment to the FPGA design. Okay. So what's the benefit of a Caravel FPGA? So you can validate your design much faster at the hardware speed. Okay, and since it's run at the hardware speed, you can run real application on the PS side. Okay, before you tape out the chip. Okay, before that you have to run very slow simulation. You really cannot run the real application. Yeah, right now since it runs so fast at the hardware speed, so you can actually run the application. And also you can use the FPGA-rich peripherals, okay, to communicate with the outside world. For example, the pink Z2 board has a network interface. That's why you can run the Jupyter Notebook remotely to access your FPGA. Okay, the FPGA HDMI interface, you can render your display output and see it. The FPGA has a lot of I/O pins, so you can connect with your sensors. Yeah, the sensor can get the data and feed it into your test chip. We have to run very fast. Okay, so the lab platform. Okay, right now we are talking about the validation platform. Okay, and we have a talk about this. Okay, inside the user area, I embedded a few IP to communicate with the FPGA, and this is the IP we implemented. Okay, by those collaborators in the academy, and this is your user project. Okay, so when you tape out the user project, you put in those IP, and that's open source, and those design has cost very little gate counts. Yeah, and so that you can design your user project using standard XI interface. That's very important. And in today's in the Caravel SoC, you could not design your IP using standard XI stream XI interface. With this infrastructure, then you can design your IPs through the XI Lite and XIS to transfer data. And this standard IP can be easily and readily integrated with standard SoC design. Okay, all you need to do is get our open source IP, put into in your user project area. Okay, so benefit of FSIC. So we use this platform to train the full stack IC designer. Okay, and so you can using this platform to validate the system and application system level validation, and also, as I said, it's scalable development. Okay, so you don't need to design your board, and a lot of people can share the lab facility remotely. Okay, so through this FSIC, we realized the ultimate goal of Google open source silicon, easy to design your IC. Most importantly, it's easy to validate your IC. Okay. So current planning is currently, I led 20 collaborators from academy to develop this FIC, and we will tape out this chip in November. So one announcement is currently we still lack of the user project. We develop all the IP around it, but this user project, I put very simple FIR filter, but it can be put some more meaningful user project. So if anybody would like to contribute on the user project and take this free tape out, but we are using chiplet, we will pay for it. Yeah. And also those platform I developed will be used in the course SoC design in these 3 universities as a lab platform. So people gonna to go through all the development process in this SoC design course. Okay, my future plan is see whether it can connect with the employer. Okay, let them to recognize or even endorse this FSIC program. And I would like to extend to low underrepresented people. In here, underrepresented means those people who are not WECS background. Okay, they are probably a mechanical engineer or chemical engineer, whatever. Okay, as long as they have a logical mind. Okay, I think everybody can do the IC design. Yeah. And I hope that this program can also extend to the industry on-job training. I believe a lot of the IC design house, the engineer they hire, they don't have this sound system knowledge. Maybe they can send their engineer in this FSIC program. Okay, this concludes my talk. Any question? Oh, yes.
Thank you for your very impressive talk. And actually, you said that the PDK and the process is mature enough to not need for the chip verification, but you need system verification for more.
Yeah, those are 2 separate issues. One is the
IC
manufacturing.
Yeah, yes, I know.
I am now addressing the issue.
Okay.
Now the PDK
Yeah.
yeah,
because yes, but the point is that if we go with open source EDA tools, the tool is not so mature yet, I think. So that the chip verification is also required. So I want to make test vector or something like that. So
okay. I think it has been hundreds of chip tape out.
Yeah.
Using the open source EDA tool.
Mm-hmm. Yeah.
I think.
But I think there is not the test vector generators yet in open EDA tools. So test vector generators.
Oh, test vector generation.
Yeah. It's a big problem.
No. That's not a big problem. Yeah, the test vector generation is pretty easy and straightforward. You run the simulation, you capture the I/O signal pin, and convert to the test program. I wrote that program before. So probably it's not the critical issue. Yeah, so the tester simply capture the I/O pin and you define time state and then expected value. Yeah. Although I did that 30 years ago, but today I believe it still probably follow the same discipline for test program. Yeah, so probably it's okay. Yeah. Any question?
I think that if you have a question, maybe because everyone.
Oh, it's coming. Next session now. Okay. Yeah, thanks. I will stay here. Yeah, you can come to me